Hey Opties! Today we're looking at non-rigid transformations of functions. We have representation of these in equations and in graphs, and we're going to look at some parent functions and see how a stretch or a shrink/compression will change the parent functions. We have stretches for vertical and horizontal, and then we have shrinks/compressions for vertical and horizontal as well. So let's take a look at our first one, stretches. Vertical stretch. Okay, so if we think about if you're stretching something vertically, think about silly putty. You stretch it vertically. Your x values won't change, but your y values are going to get bigger because you're getting taller. You're stretching it, you're getting taller. So that's what we see here. The way we identify a vertical stretch is a number being multiplied on the outside. So it's being multiplied by f of x. So f of x goes to c times f of x, where c is just some number. And this would be looking at the absolute value of c. Notice it says c has to be greater than 1. So if it was negative, the negative sign would indicate an x-axis reflection. So we're only looking at positive numbers here. And if it's a stretch, it's specifically greater than 1. Think about if you were equal to 1, you wouldn't change anything at all, because if you multiply by 1, you stay the same. Again, our x's stay the same because we're just affecting our vertical numbers, which would be our y values. And so the y values get multiplied by whatever number goes with your vertical stretch. So if we look at our parent quadratic, it would look like c times f of x, which would be c times x squared. And notice our dark green, which is our transformed function, it's a little bit skinnier than our original function, which would be our parent function. So if you stretch, you get skinnier. Think about, this is like kind of a weird example, but like, at least for me in middle school, you know, you still have your baby fat, you're a little bit pudgy, and then people sometimes say, well, they stretched out, you know. They kind of grew into themselves, you know? You stretch out, you get taller, and then your baby fat kind of like goes away, or it kind of gets distributed. So if you're getting taller, you're getting skinnier. That might be a good way to remember. Let's look at our square root of x function, parent function. That would be c times the square root of x. And see how it gets taller. It's a little bit harder to think about it as skinnier, because we got two sides of our parabola, right? So we can see it gets skinnier. But regardless, you're getting like taller for our square root of x. If we look at a cubic, y equals x cubed, or f of x equals x cubed, and have a c times x cubed, we can see here that it also looks skinnier. Let's take a look at horizontal stretch. So the first thing that I would think about horizontal stretch versus vertical, besides the change in direction, is that for vertical stretch, c is greater than 1, and for horizontal stretch, c is between 0 and 1. So this would be things like c could equal 1/2, or c could equal 1/3. So this is a loose way to say this because it's not always true, but people kind of think, okay, fractions. But you could have a fraction that would still be greater than 1. But fractions that are between 0 and 1, these are going to cause a horizontal stretch. Now to me, it's kind of weird, because with stretch, you would think you're getting bigger, right? Well, remember how we had a plus, a number on the inside of the parentheses was horizontal shift for our translation, but it was to the left, even though it's plus. And if it was a minus, it was to the right, even though it was a minus. So it kind of swapped the direction you would think. Same thing with our horizontal stretch. You would think stretch means bigger than 1, but it actually means between 0 and 1. So it's kind of a swap thinking on horizontal, just like our translations. So for our x squared, see how we're getting much fatter. Because if you're stretching horizontally, you're getting wider, right? Looking like you're getting a little bit chunkier, fatter, wider. Wider's the best way, right? And the square root of x, see, you've got your c on the inside of your square root, just like you had your c on the inside of the parentheses for your x squared. Now it's gotten shorter. You stretch it horizontally, it kind of makes it a little shorter there. Stretch it vertically, you're getting taller. So you can see the relationship there. And for f of x is x cubed, we're still getting wider. It looks more similar to me to the parabola. Still the same relationship, but it's a little different for our square root of x because it's not like got two sides to it like our parabola or our cubic does. Let's take a look at compressions. Some people call these shrinks. I used to kind of like shrinks better, but now that I think of it, I think compressions makes a little bit more sense. What I think about is, you ever seen those videos? They're like super awesome to watch where they've got this really big compressor. And they're taking all kinds of objects and they compress them. And you just see them go bleh. They like get crushed basically. So to me, that makes more sense when you're talking about these compressions for your functions. But shrink also works for that wordage. So we have vertical shrink or compression, and that's going to be like you think it would be between 0 and 1, because compression, you're getting smaller, it sounds like, right? So f of x equals a c on the outside. So it's still a c on the outside being multiplied by your whole function, just like your vertical stretch. But the way you know the difference is how big c is. If it's between 0 and 1, then it will be a shrink. If it's greater than 1, it would be a stretch. Your x's stay the same because this is affecting our y values. So shrink would be like taking it down like this, right? And you got a c times y, so you're multiplying your y's by that c value. So notice that if you look at our vertical stretch, we're getting skinnier. If you look at our vertical shrink or compression, we're getting a little fatter. But notice it's not quite as fat as our horizontal stretch. So if you had the same number c on the outside that you did on the inside here for this x squared, the horizontal stretch would actually be a little fatter than how fat the vertical shrink or compression would be for your x squared, which is interesting. So if you look at our square root, we see our dark green is the transform function here. And again, if you're vertically shrinking it, you're shrinking like this. So you're going to get a little bit shorter down from vertical shortness, right? So it looks below the apparent function line. And for our cubic, again, it's a little bit wider. You're squishing it, it gets wider, but it's not quite as wide as your horizontal stretch here. Let's take a look at horizontal shrink. So horizontal, again, remember that's our left to rightness, our x-axis direction. If you ever get vertical and horizontal mixed up, just think about horizon. It's the horizon line, and that goes with horizontal. So that's going to be a c on your x, so c times x, but c would be greater than 1 here. So you multiply your x values by that c value. For your parabola, it gets skinnier, and it's skinnier than a vertical stretch. For your square root function, it gets taller, but it's not as tall as your vertical stretch for that. And for your cubic, it gets skinnier, but skinnier than your vertical stretch. So the reason we would compare a vertical stretch with a horizontal shrink is because they're kind of pulling the function in the same direction. It's not the same thing, but it can look very similar. Because a vertical stretch, we're getting taller. A horizontal shrink, you're squishing it together. So either way, you're going to get skinnier, right? But again, they're not the same. Notice algebraically with your function, right? C times x is different than a c times f of x. All right, Opties, that's it for non-rigid transformations for our functions, which includes stretches for vertical and horizontal and shrink/compressions for vertical and horizontal. See y'all next time.